Okay, hi, I'm Bob. I think in the last minute you all had a chance to buy this, right? Everybody did? Okay, good. Good start. So let's talk some glue. Right, we are looking for glue here. So I'm going to talk about a pictorial formula for quantum system, which you find in this book, which I've been spending a lot of time working on. I'm going to talk about natural language meaning composition. Seems like a totally different subject. But like, well, it's almost now 10 years old that we've done some work on that, and which actually got me very high up in the crackpot index of some bias, I guess. Right? They all quantum linguists and all that stuff. I'm going to talk about compositional cognition. So this is, I mean, the way I see this is more really like modeling human thinking and AI and stuff like that, which is a more recent development. Also Fabrizio, who's there, worked on that in his PhD in that area. And I'm going to talk about quantum compilation, because in the recent years, suddenly, at least from the perspective of industry, quantum computing seems to be happening, from the perspective of investors at least. And we need to keep it like that. Right, okay, so let's start glue. First I'm going to talk what is really the glue for me, and that's the concept of a process theory. And I'm going to illustrate it in quantum because that's how we came up with it. And basically, this book is a book about process theory, the idea of process theory, which is our way to sell category theory haters, something like that. The skepticism. Okay, so process theories are about processes which we write as boxes and systems which we write as wires. And anybody who works with systems knows this sort of pictures, right? It's not really very strange. So here's an example from physics. Here is an example from computer science of a process. Here is the process of English cuisine in its entire richness. And this is another process. We can all do that one, or we can produce that one. So I went to my hotel last night. I always have a drill on me because I'm now a fully skilled builder. So I use a lot of glue actually in my daily life. And then I brought all these ingredients, and then I composed them to do this and to decompose my hotel room, right? So that's what I did. So this is what basically process theories are about, composing stuff. So that's where compositionality and all that comes in. So here basically you got the entire structure. That's what it is. That's what it is. Right. Stuff you don't want to compose, and that's why composition is important. Like, I mean, you can throw your machine away if you do this, right? You understand that? You shouldn't do that. So it's very important what you compose. Okay, so one thing you get in such a theory is the idea of tautology, which are, so basically, in this process theory, the sort of mathematical structure we're talking about is the notion of a diagram. And what's a diagram? A diagram is a bunch of boxes who are connected in a certain way. And from that point of view, the left-hand side and the right-hand side are just the same. So this is really a tautology. Mathematicians would call these free equations of the theory, but I prefer the word tautology. Because it's really a tautology. Now, process theory is there where you put in some more data, and it consists of a collection of systems, a collection of processes, and it formalizes wiring things together. Basically, it's an interpretation of your diagrams. What are my boxes? What are my wires? And actually, the tricky thing is what it means to wire things together. That's actually where it becomes a bit more complicated if you go to actual mathematics, and you actually need to use category theory in its more traditional formulation to connect such a process theory to the mathematics you're used to. I'm not saying mathematics that's good. It's in the mathematics you're used to. I'm not sure whether it's good. And so it in particular tells us when two diagrams are non-freely equal. So here is an example of an equation which you would find in a process theory, which is not a tautology. Right. There are some special concepts in the process theory, like the idea of state of a computer, state of a quantum system, effect, which is sort of corresponding to measurement or testing, and numbers, because we want quantities, we want probabilities. So they're all living there. And then we got something which you could call a generalized border rule. A border rule is something from physics, tells you how you get probabilities. And when a diagram without an input and a diagram without an output meet each other, you get one without an input and an output, and that's a number. That's how you compute numbers in physics in this sort of language. Right, let's look at now special kinds. So we got the general notion of diagrams. So what we want to do next is understand how you can have special theories with special properties just by saying what kind of diagrams we're working with. And to this extent, it can be useful to introduce two operations on diagrams, which actually I'll also put in my slides to show you that this is related to category theory. Basically, what I'm building here is the structure of a monoidal category. So you can actually put two diagrams side by side, which is totally trivial operation. And you can put two diagrams one behind the other, which is slightly less trivial because the inputs and the outputs have to match. And one can then, I don't know whether this is even a good name, that's the name we use. We call a circuit a particular kind of diagrams which are built by means of these operations, really which you build with while and after. And actually, circuits are really boring, so I'm not going to talk about circuits at all today because it's useless and boring. So what is the interesting stuff? Well, the interesting stuff is something Schrödinger, a long time ago, was already dreaming of. So this was sort of at the same time as von Neumann started something which was called quantum logic, and which was 3 years after von Neumann publicized his book on the mathematical formulation of quantum theory, which we still use in terms of Hilbert spaces. So von Neumann's focus was always, and most of the community's focus had always been, like, we need to axiommatize and formalize quantum mechanics by focusing on the concept of measurement. It's the way we interact as humans, as laboratory people, as observers with a quantum system that actually makes quantum theory fundamentally different than classical physics. And that's anybody who's got a quantum theory course, they will have learned that. Actually, Schrödinger, very long ago, was already thinking differently. He was thinking, what's typical for quantum mechanics is what happens actually if you put two systems together, and how that is different from what happens if you put classical systems together. Now, how do you so the von Neumann thing kind of led to quantum logic, and they were saying, yeah, the logic of quantum systems is different than the logic of classical systems, blah, 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 blah. I worked in that area too, which was a total failure, one must say. So I was in the gutter and everywhere. I've seen the lowest of the lowest of society, by doing quantum logic. So then I tried to go even lower by doing category theory, but miraculously, actually, category theory suddenly became something. It was a big disappointment because I like to be on the ground and margin and all that, and I failed. Okay, anyway, so how do you realize Schrödinger's dream? How do you realize Schrödinger's dream? Well, you need to come up with a mathematical structure which at a very fundamental level talks about what it means to compose systems in a non-standard way, possibly non-standard. And that's really what these diagrams and these process theories do. Because the moment I write two wires side by side and saying, hey, there's two systems here. That's all. Just writing two wires side by side, I'm talking about two systems. Now I want to say in some way that these systems are actually quantum systems and not things which are described by boring circuits. So how do you do that? We have two equivalent ways to do that, and the first one is actually closer to how you find it in category theory text and category theory textbook. And this is what's called a compact closed category in category theory language. Basically, somebody said something?
No, that was okay.
Okay, there you go. So basically, we assume that we've got a very special state, two systems, and this state will witness the fact that this is not just a standard pair of two independent systems, but actually behaves like quantum systems would behave if you put them together, and a corresponding effect corresponds to that. And they obey. You see three equations here. Ignore the two ones on the right, which just say that these things are symmetric. So if you swap them, then you get the same thing. The first equation, that in some way, by means of that state and that effect, you actually realize an identity. Shut up in the back. Right? Okay, good. Yeah. So you can actually realize an identity by means of state and effect, which what are classical systems in this language? There are two diagrams with one wire which are not connected. They're disconnected. And basically what this equation is trying to axiomatize the idea is that these things must be connected, because in some way by configuring them like that, actually why. Now, this is much clearer in my other way of defining the same thing, which is not by putting in a special state and a special effect, but by being really liberal about which diagrams I can write. And I mean, I didn't say anything about inputs and outputs so far, but now we will allow diagrams from outputs to outputs, from inputs to inputs, that an output in the future can be connected to an input in the past. It's a very liberal sort of diagram, the sort of thing I think you call string diagrams. You were the first one to maybe come up with that name, right? Possibly. No? Joel? Okay. Right. Anyway, that's the thing. It's very liberal. It's much easier to define it like this than like this, which is the standard category theory way. But I mean, it's the same thing. And the way to connect the two is basically to think of this triangle state just as a cup-shaped wire, the other thing as a cap-shaped wire, and then your equations become totally trivial. I mean, they're just what it means to be a wire, nothing more. They just tell you what it means to be a wire. Okay, you get things like cyclicity of the trace becomes tautology, total tautology, and quantum teleportation, which took 6 people 60 years to discover since the start of Hilbert space formalism, becomes also total triviality to discover. So you got Alex, okay, Alex, this is the guy I wrote the book with, and Bob. They share a cup state. They want to get the state from Alex to Bob, like that. How do you do this? Oh, just a piece of wiring. That's it. That's how you discover quantum teleportation. 60 years to discover. Anyway, we move on. What about natural language meaning? Total change of subject. Okay, the question we were trying to solve when we started working on that was, there are dictionaries for words, right? So why are there no dictionaries for sentence? Why do you understand a sentence when you actually never have heard it before? This is the answer. It looks quite similar to this sort of teleportation thing, right? It's clearly a wire diagram. So basically, what does this picture mean? Well, it's a picture about meaning and how meaning interacts. So in the top bit of the picture, the dotted line, that actually represents grammatical structure. The bottom thing actually represents meanings of words. Some of them are structural because they are themselves wires and things like that. But they're actually meanings of words. They could be vectors, like people mostly use in modern day natural language processing. But the key thing is that in most natural language processing tasks, grammatical structure is not taken account of directly. And what we have here is a mechanism to make the meanings and the grammar interact according to what actually grammar is supposed to be. Right, so how does this work? Let me give like a brief. I mean, this is all going to be very brief. But so the mathematics of grammar, in sort of, I mean, it goes back to Chomsky. Who knows that, the sort of more formal category theory side of it. And in a way, I mean, it's fair to say that Lambert co-invented category theory, right? I think it's a fair thing. At least he invented monoidal categories. So the first thing is something you find in papers of Lambert's in the 1950s, and that's now called the Lambert grammar. And in category theory terms, it's a thin, non-symmetric, so basically nothing, no braided, non-symmetric, nothing, non-commutative, monoidally closed category. That's it. Thin one means you got a partial order. Well, you got a pre-order actually, instead of actually having morphisms. Now, 50 years later, same Lambert realized that's not really the right thing, the thing we want to do grammar with. Came up with something else which looks like that. And you may not see it immediately, but these are actually my cups and my caps and my wires and my string diagram, written in partial order terms like the thin case, and Lambert called this a pre-group. Because it's pre-group because you got a left and a right inverse which are all the same. So that makes it not being a group. And unlike the sort of compact closed categories I've been working with, this one here, they're not symmetrically either. There is no symmetry or anything going on. Otherwise, it becomes totally useless for language because order of words in a sentence is usually important, right? Okay, so this is this thing. So you have to think about this as a compact closed category thing at the bottom. Now, how does this work? I think most of you must have seen this. So basically, you got a number of basic types, which are types like noun, and actually sentence is a basic type. And from your basic types, you can actually build composite types. Like a transitive verb is a composite type. What is a transitive verb? Transitive verb wants to be a sentence. It wants to be a sentence, but in order to become a sentence, it needs a noun on the left and a noun on the right. And then it can actually fulfill its dream and become a sentence. That's what you see there. You've got a S for sentence in the middle. You've got N with a -1 on the left, asking for a noun on the left. You've got N with a -1 on the right, asking for a noun on the right. And then you can do a little bit of calculation. You stick a noun in on the left, stick a noun in on the right. They cancel out by just standard algebra. You see that the right type of the combination noun, transitive verb, noun is sentence. That's what you want. That's how this stuff works. So basically, we make a computation there, but you can actually represent this computation as a diagram, which I'm doing here. You see, the sort of like a mathematician, if they see n and then n minus 1, and they cancel this out and they scrap. We're not going to do this. We're going to use like a wire shape to say they annihilate each other. Like they annihilate each other. So it's n minus 1 annihilate each other. The sentence goes through, n minus 1 and annihilate each other. So this is a representation of the calculation you see up there. But I want to now treat this as a function, not a function, as a morphism, as an operation on stuff. On what stuff? Operation on meanings of words. So in the same way as these caps and these cups in the quantum theory would represent linear maps, things in Hilbert space, if you represent these Alice and Hades and Bob as vectors too, then basically you can think of these cups and this identity as a linear map too. So we got an algorithm here. You take vectors for Alice, vectors for Hades, vectors for Bob. Doesn't matter how you build them, there's standard ways to do that. And you apply a linear map to them, and that's going to be your meaning of your sentence. That's basically how this thing works. Before that, the only compositional theory about meaning was Montague's. But Montague's theory is a propositional theory. It's about truth and false, and it allowed you to sort of derive logical truths from logically formulated sentences and falsehoods, even other sentences. But in language is more than true and false, of course. So you need richer, and this sort of framework is sort of blind to underlying. It's categorical. It's blind to the underlying model you use to model language. So okay, this is the algorithm. Kind of just explained this to you. At the time, people, some collaborators of mine, they did some experiments and they outperformed whatever else was available at the time. Now, meanwhile, of course, machine learning people, or fucking machine learning people, like Rodrigo would say, they have done better. Because we kind of were sitting on our ass and writing a book and not really bothering too much, competing with them. Because you have to be smart. You don't want to compete with power. You want to compete with cleverness and think of clever ideas. Anyway, so what's also nice about this picture, which I showed you in the beginning, for example, that it's not just about looking for vector meaning by empirical means, which is what people usually do. You get some logic in here. You see the word does, and you see the word not. They're actually logically formulated by means of wires. Ignore what is pi is. This is like actually not. This comes out of this is actually a pi phase from quantum mechanics. Don't ask me why, but that's actually what does the right. So you get some logic in here, and this is now just for the words does and not. But like if you start doing relative pronouns and other things, you actually get more interesting categorical structure. Will also become part of the language. Okay, so this was all about NLP, and so we were selling this at a time as natural language stuff. While I think it's much more fundamental than that anyway. So instead of natural language processing meaning, you can think of any kind of meaning. It doesn't have to be natural language. It can be meaning is a much more richer concept than natural language. And examples are, if you replace your vectors with, say, Boolean matrix, you get Montague semantics. Interesting thing, if you go to vectors and all that, logic actually dies. So what I'm now starting to do is playing with different models of meaning. Because that's the game you want to play. But then we tried density matrices, which again something which comes from quantum mechanics, and then logically emerges, and we did experiments with ambiguity and logical exploitation. Because in a vector space where people standardly represent meaning, you can't really say that a tiger is an example of a big cat, and a big cat is an example of a mammal, and a mammal is an example of an almond. You can't say this in vector space. There's no entailment structure because sort of a flat structure. Density matrix, for example, allow this. I mean, we just did it because it was available. But actually now we want to go to cognition. So we're going to go to cognitive thinking. Okay, cool. So what is general recipe for now? You pick a compositional mechanism. You organize meaning, concepts, cognitive stuff, whatever in a tensor category which matches the same structure. And then you really map your compositional structure on your meaning thing. That's sort of a general recipe. And the way we did this is we went to the library, not me because I don't read, but I sent somebody to the library. and said, who's one of the most famous cognitive scientists now? And they came, oh, that's Peter Carroll. They said, okay, let's read what he's doing and make a compositional theory out of whatever he has done. We did something similar with Smolensky, but I'm mainly going to talk now about Gardenforth stuff. So this is actually being discussed now on the N category theory cafe. This stuff. I mean, the previous stuff was discussed a few weeks ago, right? The language stuff on the N category cafe. So this Gardenforth stuff and our compositional theory is now being discussed on the N category theory cafe. Right. So basically, what we need to do is we have to come up with a monoidal, with a compact closed category of the sort of stuff he likes. What stuff does he like? Convex spaces. He thinks of meanings as living in convex spaces. So we need to come up with some category of convex spaces. Maybe we got this guy, Dan Marsden, some sort of monad obsessed guy in our group. I say, we have to do this stuff. Okay. So we do this stuff. So we get ourselves a theory, and then you actually, instead of vectors, we are now starting with subsets of convex shapes. Like, for example, color. What is color? Color in this sort of conceptual spaces theory is a subset of whatever color shape you have. I mean, usually you've got sort of, how is this called? Like a circle with a top and a bottom, how do you call this shape? Good, that's the usual one, but we found it too difficult to draw, so we cube. Well, it doesn't matter really. And actually, like, taste is not a tetrahedron, but then again, with 5 coordinates, it's hard to draw, so we just kept ourselves to 4. But you see the idea. So green is a subset of that thing. Yellow is a subset of that thing. Then you got where taste is a subset of these convex things. And then you can give meaning to a banana and an apple and a beer. And then you want to start reasoning compositionally with these things. However, to make this interesting, you need a bit more extra structure in your structure of natural language. So we go back to quantum mechanics to get some inspiration. And it's about glue. So these are spiders. Technically, they are special dagger commutative Frobenius algebras. I probably forget one of the words. Did I? No, I think I'm right. But ultimately, the way I think about them is as multi-wires. So what is a wire? A wire is a thing which connects 2 ends. And then you can connect 2 wires together to make a longer wire, by putting a knot. You take one end from one end from another, you make a knot, and you get a long wire. So spiders are multi-wires. They don't have 2 ends, they have multiple ends. Now we take one end from one spider and then another spider, you knot them together, you get a big spider. And that's really what's happening here. So these nodes represent spiders. 2 spiders meet each other, they are connected in some way, you get a bigger spider. So that's the sort of key equation governing the behavior of these spiders. And they are a generalization of wires. And Dushko, sitting in the back, who I think talks later today, we sort of came up with this to actually represent classicality within quantum. So you want to show what is an outcome, what do observers see in quantum theory, and that's classical stuff. So we came up with these spiders to use it, and then later we showed that actually it wasn't just a matter that it works well, that they actually are canonical in the sense that they exactly, this algebraic structure when representing in Hilbert space, they exactly correspond to orthonormal bases, which is actually what classicality is in quantum mechanics. So we have the right thing, so we worked further with them. We can now do teleportation. I mean, I'm not going to go in details. You can read this in my book, which you all bought half an hour ago. So I don't have to talk about that. So what about meaning cognition? Bang, here you see our spiders. So we use spiders to represent, for example, relative pronouns and other sort of logical structures of language. We can now say something like, gee, who hates Bob? And then you can encode this with, say, for example, density matrix model. She who hates Bob is Alice, and you compute that stuff. This is really a computation. And now we can also now start computing with our bananas and our apples and our beer. Oh, yeah. And then, for example, you can ask questions like, what is he, like say things like yellow banana, or ask questions like fruit which tastes bitter. You compute the whole thing and you get a green banana. Does that taste, does a fruit taste bitter? So you do these computations now. And these are not vectors anymore, these are like these weird shapes living in this convex stuff. And that's what we compute with. So Gardenforth, the big guy, he saw our stuff and he loved it, and he gave a talk about our stuff. And he said, what we have to do next? I said, okay, yeah, we'll do it next because you're smarter than us. So something we are now working on entanglement or superposition of meaning and grammar, because meaning and grammar are actually defined. You can't sort of separate them out entirely. Don't have time to go to examples. And another thing is like, another very important aspect about meaning in the way we think is spatial representation. Like my computer is on the table, you're sitting on a chair, you're in front of me. It's all very spatial. So we're actually, I actually did this on the plane here to come up with a good model there to actually represent that stuff, which is different than the sort of convex stuff, which is complementary. You can put it together, but it's really, prepositions are typically very spatially related. Okay, so bang, bang. I think I've got 3 minutes left. Am I about right? Yeah. So, okay. So far I've talked about in my process theory language about wires and multi-wires, which are spiders. And so we've done some stuff with them. We represent classical structure in quantum mechanics. I think we didn't do this here because of time. We represent language structures, we do the same thing. So we actually go a bit further usually because our goal was to come up with a fully diagrammatic representation of quantum theory as a whole, like fully expressive, that to be universal. You have to be able to write down any matrix as a diagram, as a picture. And then we actually wanted more. We didn't only want to mimic Hilbert space, we wanted a calculus, which is which can actually reproduce any equation between matrices. So we already went to spiders, right? Then the next thing we do is we decorate spiders with like nice, beautiful, spiders usually have nice, beautiful decorations, right? So we did that too. And this is not actually a new structure. This comes really as part of the structure of a spider or categorically of the Frobenius algebra. They always come with some commutative group structure on top of them. And that's what these decorations are. And then we said, okay, one color is boring, let's do 2 colors. So we had spiders of 2 colors, and they sort of interact in a way with each other. And it turns out this is what's called a pi algebra. So there's like very strong physical reasons to believe that they interact via pi algebras with each other, which is not something the physicists knew about by the way. Anyway, then we came up with some calculus, Z calculus. That's something in 2008 we did. But this couldn't reproduce any equations between matrices. And then recently we had this enormous activity of people, like they're mostly PhD students of me or former postdocs, and they came up they came up with rules which allow you to reproduce any equations you can reproduce in Hilbert space. And I mean they're still busy now. Like, it's just happening now. Oh, it's amazing. It's amazing. Wow. As a result of all this recent progress, we're now working, because it's applied category, we are working with a quantum computing company who's giving us money to do this sort of stuff. And this is called Cambridge Quantum Computing. And basically what we're building are architecture independent, very efficient, and in an exact way, like we can actually produce equations diagrammatically quantum compiler. Because quantum architectures, quantum computing architectures are not like classical computing architectures. Depending on, and they have all different fault tolerance properties and all that, so people are just trying all of them, and your compiler needs to be able to translate between them, and some are like very parallel, other ones are very sequential, and our pictures, these diagrams, they can just be reshaped from sequential to parallel and all that, and that's stuff we're doing there. Okay, like if we do search, right? Okay, now just in my last 30 seconds, I want to do something more fun, which I'm doing too. I don't know how applied this is, but I mean, how old do you have to be to start that stuff? Yeah, how old do you have to be to do these things with these wires and these boxes? Huh? I mean, I don't know. That's my daughter. She's reading my book. You know, she bought a copy, you know. So you better. Right. So we're actually doing experiments in the summer, something which I proposed a long time. So we're actually going to teach high school kids to do quantum physics with these boxes and wires, and then we're going to take a bunch of like posh Oxford twats, like that's Boris Johnson's in there, for example, and we're going to teach them usual quantum mechanics, and then these kids are totally going to outperform these twats. So that's cool, right? And then we get nice New York style, like sort of heading kids outperform Oxford twats, and discover quantum features that are 60 years. That's what we're going to do this summer. Okay, that's it. Thank you.
You have a couple minutes for questions?
So Piaget did experiment.
Piaget, yes.
But his conclusion was that teenagers most amenable for categories.
But that was his conclusion. I mean, there are some really weird movies which you find online from Oppenheimer citing Piaget, and they were working together on like the role of topology in the way kids are thinking, and probably that's the sort of age where René Thom was also a strong believer of these sort of things. So basically, I've got no background in it. It turns out my wife does this sort of experiments. So like as like a nice case of super corruption, my department hired my wife working on these things because say you can't do this, you know nothing about it. We have to hire you. Okay, thank you. So, but you're totally right. So she's working at UCL, University College London, doing these sort of experiments. What are the best ways to teach maths to kids? Although she's working with much younger. So, but we are thinking high school. We're thinking high school. Let's see. I mean, it was a lot of work because we had to write a tutorial for these kids, a tutorial in open space, which nobody can argue. There's no bias to make difficult or easier than the other, and we have two sets of exam questions formulated in different languages, but actually the same question. And then we're going to see what happens.
Yeah, how do you treat a noise in quantum systems? How do you model that?
Open
quantum systems.
Open quantum systems is very easy because of the compositional nature. I didn't represent this, but there is something Peter Selinger came up with, and we call this CPM construction. Basically, what you do is you double your system. So you've got your box, you make two boxes, and then you connect them. And the connection is like the openness. It really mimics again von Neumann's construction, which is like from a vector to a density matrix, you just double. And then you do a sum, and the sum is the wire in the middle. So it actually works very natural. The thing is, for most of the calculations which I'm doing, you can think of them as open systems anyway. It's just when you actually want to use the extra structure of an open system, you have to do it explicitly.
So the different channels are different wires.
Yes. So we describe this in detail in our book, and things like nymeric dilation become totally trivial theorems in this language. Well, in C-star algebra, it's complicated. So here it becomes totally trivial. Stein-spring dilation, all these things become very easy. I think it's one of the big options. These open systems become easy. Well, usually they're very different.
From the logic standpoint, when you do your NLP, you're kind of forcing the sense of those simplistic being orthomodular lattice. When that might necessarily, you're forcing whatever you're looking at to be an orthomodular lattice. That might necessarily be the case. So I'm wondering if, computationally speaking, that what you have is a very nice system. However, it might not actually come to the logic of what somebody actually said. Maybe in more complex situations.
This is really problematic issue. If you work with vector spaces, logic is completely gone. Vector spaces and logic just don't go together at all. You got some sort of linear logic there, but the linearity is totally against like your Boolean aspects of logic. You don't find your Boolean collector. So you said modularity. So what we did, but this is just like I would say an engineering thing, state density matrices, where the projectors sit as an modular lattice, but actually you can extend this orthomodular lattice, include all density matrices, and it's still an ordered structure. So you can use it to encode entailment. This is actually quite new, ordering of density matrices. This is not something that was around in the quantum literature. And then you can use this to, for example, encode lexical entailment, tiger in a big cat and all that. And the nice thing is, of course, density matrices themselves, they still live in a bigger vector space, so all your empirical methods still work. And all your techniques for vector space still work, although it's bigger. You need a bit bigger computer to compute. That's the only downside. Nice thing, if you have a quantum computer, it's all automatic, isn't it? Because any system has the structure automatically anyways. Then you get the extra dimension thing. We got some algorithms specifically for this thing, which would, of course, give a serious speed up on quantum computers. For the reason of the glue aspect, that we use exactly the same language for the quantum as for for the natural language stuff. So you would expect to see this benefit from doing it like that, and you get these informed computational